skin above.
It's time for us to discuss something that we probably should have already talked about, and we've even run into it a little bit, but it really requires a more complex model. For instance, a model like this, where we don't just have y equals mx plus b, we have 6 different slopes and 6 different x's. Now keep in mind that when I say these x all have a different number, it could be that x2 is the x1 variable squared. The computer doesn't care. It goes through and does the math and just calls this a new x. We could have interactions, we could have categorical variables, all the stuff we've talked about before, but this is a linear model where we have each of these separate pieces. And maybe not every variable needs to be in the model. So how do you pick which variables should be there? How do you get to your final model? And we've already talked about one of the biggest rules, which we're going to explain why you should only remove variables one at a time. So let's pretend we did an analysis with each of these variables, and we want to look and see whether they're significant, meaning should they stay in our model or not. Notice I don't really care about the p-value for the intercept. I'm just using a value that I need in order to make my model work. So these guys are the ones I'm worried about. Should I keep these variables in? Does x1 help us predict y? Well, small p-value says yes, it does. But it's the only thing that helps predict y. And your instinct is to say, let's delete everybody else. The problem is that if I rerun the model without one of the variables, all the other p-values change. Why did I pick this variable? Well, he had the biggest p-value, so I chose to run it without him. And now, all of a sudden, x3 is significant. The slope on x3 does matter. The p-value here was big, meaning your model does not change a whole lot if you throw it out. But that p-value is not testing whether all 5 of these are significant to the model. So it turned out that without this extra noise and randomness in the data, we could see the effect of x3 better. And so yes, it was significant. What should we take out next? Well, I'm seeing a big p-value here. Let's take out x5. When I do that, these p-values will change. The way you get these p-values is you actually literally run the model with and without that variable. And then you ask yourself, did the model with the variable in there have better predictability? Well, no. 65% of the time, if that variable is meaningless, you would get an improvement in the predictability like what we saw. So this guy really doesn't have much evidence that he's helping the predictability. But that's not the same as saying all 3 of these guys should be taken out. That would be a different model. And if we wanted, we could talk about how to do a test of all 3 of these guys at the same time. We're not going there. We're looking at p-values that test one variable at a time. So if I want to know whether I should have beta 4 in the model, I'm going to take that beta 5 out first and then recalculate a new p-value. And now it's completely different. Why is it completely different? Because this beta 5 is now not in the model. We're comparing completely different models than we were before. We've compared this model to that model. That's how we got this p-value. This model to that model gave us that 0.65. And we're comparing a model without beta 4 to this shortened model with beta 4. And it turns out, yeah, it is needed. It really does make a big difference. So you need all 4 of these variables. Notice that when the p-values jump, sometimes they don't jump, and then sometimes they jump a lot. Look here, this guy jumped to 0.02 and then stayed the same. He was not significant, suddenly was. This is not unusual. Now, how does this happen? Well, here's an example. Let's say that we had a variable which was measuring your height in inches. And let's add on a variable that is measuring your height in feet. Can you tell this is a bad idea? If I know your height in inches, does adding your height in feet actually give me any knowledge? No, it's the same thing. All you've done is change units. These 2 variables are telling me the same thing. In fact, if you try to do this in R, you'll get a little error saying, yeah, no, there's no extra variability here to help me map what I'm predicting. So clearly having both variables in the model is useless. You should kill one of them and kick it out. But what if they're not exactly the same? They're just related. Here we have your height in inches and your weight in pounds. And there is a relationship. If you tell me how tall you are, I can predict your weight, especially if we were talking little kids, right? Because if you know how tall a kid is, you can make a decently good guess at their weight. So do both of these variables tell me the same thing? Well, what happens if they're related is they'll share their significance. Notice up here, neither one of them seemed to be significant because they were sharing the same error and variability. But once I got rid of one, suddenly I could tell what the other one was doing. So these two variables are what's called collinear. They both have a relationship that's linear. As you go up in height, you also are expected to go up in weight. Because one variable has information about the other variable, you might not need both of them. Only one or the other will do just as well. Because I said one or the other, it's possible there could be two models which would both work well. For example, this one we still have significant variables, but we've swapped x4 for x5. Which one is better? It's not necessarily that any of them are better. Both of them might be good models. There could be more than one way to predict y. You can either predict it using your height or your weight. Either answer is acceptable. And imagine if we cut out x2 for some reason, and we'll give some examples where you might have a reason. Well, we get a different model, but it still has significant variables. And some models might include more or fewer terms. In this one, for some reason, we killed beta 1, and now it turns out having height and weight both were helpful. For this particular scenario, even though weight and height are related, that little bit of extra information was needed. Now, what do you need in a model? You needed to have good residuals, you needed to have small p-values, or some reason why you picked the model you did. So what we're going to do in this chapter is look at how those p-values can jump around, how do we pick a model, and then how do we justify the model that we pick. And if it's hard for you to see how all this is happening, I have an analogy in the next video that will help explain why this is doing what it did. Darn it, I have 2 seconds left in the video and I flubbed it.